Hi, my name is Stephen Salisbury, and this is my presentation on regenerative braking. First, let's go over what regenerative braking actually is. Typically, brakes use friction to slow down by pressing a brake pad against a brake disc. This interaction converts kinetic energy into heat energy, which is then dissipated by the brake discs. In this situation, the energy is completely lost to the heat in the brake pads, as well as the deformation of the brake pads due to the friction interaction. On the other hand, regenerative braking converts the energy of a moving vehicle back into energy that is usable by the car. Energy transformed into electricity rather than heat. An electric motor is converted into a generator by driving the rotor rather than putting a current through the coils in order to get this effect. This is typically used in cars, like race cars and road cars, to charge their batteries for hybrid systems. The way regenerative braking works: a magnetic field is generated by two permanent magnets, and within the field, a loop of conducting wire, typically also a coil, is spun by an axle. Faradays Law dictates that because the magnetic flux through the loop is changing because of the rotation, a current is induced in the loop, which is used to charge a battery. Because the induced current changes direction once every half cycle, electrical contacts also spin with the axle, which allows the outgoing current to flow in the same direction the whole time. The induced current acts with the permanent magnetic field to also produce a torque opposing the current rotation, slowing the axle down at the same time. This is exactly opposite of how an electric motor works, where the current is run through the coil in a magnetic field, causing a torque about the axis of rotation, accelerating the car. In practice, an electric motor is just used in reverse to achieve the effect of regenerative braking. The idea of regenerative braking was developed in 1890 by Louis Antoine Krieger and commercialized safely in 1997 and 98 by Abraham Farag and Lauren Meyersk for slowing down train cars. A current example of regenerative braking is in any hybrid or electric car you see, like Tesla's. The specifications for the regenerative braking system is the same as the specifications for the electric motor because they both use the same machinery. For Tesla motors, they're rated at 6.6 kilowatts, which is how much energy the regenerative braking system can output. The torque that it's able to impart upon the axle is 30 newton meters, either accelerating or decelerating. The number of turns in the coils can vary between 4 and 6, depending on which model you get. And the max current that you'll typically see in these motors is anywhere between 80 and 100 amps. If you were to design one of these regenerative braking systems, you need a few things. First of all, you'd need a permanent magnet so that you could generate the magnetic field needed for this to work. You'd also need a battery so you could store charge and give it back if you ever wanted to reaccelerate. You need a resistor if the battery does not have sufficient internal resistance to prevent shorting. And you'll need a coil that can spin about an axis perpendicular to the field to allow Faraday's Law to take effect. For my design, the coil has 4 coils going around, made out of 14 gauge copper wire. The coil is going to be 6 centimeters in diameter, which means that the resistance from the copper is approximately 5 milliohms. The magnetic field strength is going to be around 1 Tesla, which is around the field strength that you would get from a rare earth neodymium magnet. And therefore, the voltage induced by spinning can be figured out like this. Faraday's Law states that the induced voltage is equal to the number of coils times the area of the coils times the magnetic field times the cosine of the angle times the rate at which the angle is changing. If we input our numbers, we get 4 times 1 times 0.03 squared times pi times cosine theta times d theta dt. Therefore, we can figure out our max voltage by setting cosine theta to 1 and assuming 7,000 RPM, which is the peak running speed of most electric motors. If we put in our values and convert 7,000 RPM to 733 radians per second, we get a final value of 8.29 volts. In order to figure out our induced current, we simply divide our voltage by the resistance, in this case 5 milliohms, and we get a value of 1,658 amps, which is assuming no resistor. Now this is really, really high, and typically you only really want around 100 amps, otherwise you might have other issues like wires melting. The resistor needed to get to 100 amps can be figured out like this. Our voltage, 8.29 volts, divided by our intended amps, in this case 100, is equal to our resistance, which is going to be our R, a resistor, plus the 0.005 ohm resistance from the copper wire. If we figure this out, we say that R equals 0.0879 ohms, which is 87.9 milliohms, which is, in all due respects, a pretty reasonable resistor. Regenerative braking isn't perfect, though. The speed of rotation to determine energy output, the braking force generated by regenerative braking decreases as the car slows down, meaning that physical brakes, or friction brakes, are required to fully stop the car. Also, energy capture is not 100% efficient because of material limitations, like wire resistivity and battery inefficiencies, which will cause charge to be lost. More expensive materials, like better wiring and more expensive lithium-ion batteries, help to limit this drawback, and a lot of production companies use these. So, that's how regenerative braking works. When you don't really understand it, it can seem pretty magic, but once you understand the math behind it, it all makes sense. Thanks for watching.